Let's explore logistic regression, a common classification algorithm in data science. We use linear regression when the outcome is quantitative, example, predicting sales. We use logistic regression when the outcome is qualitative, example, predicting wins and losses. Predicting a qualitative response for an observation can be referred to as classifying that observation, since it involves assigning the observation to a category or class. Example, a person arrives at the hospital with a set of symptoms that could possibly be attributed to one of three medical conditions. Which of the three medical conditions does the individual have? Another example, a bank must determine whether or not a transaction being performed is fraudulent based on IP address, past history, etc. Just as in the regression setting, in the classification setting, we have a set of training data that we can use to build a classifier. In this data set of credit card transactions, pay attention to the outcome. The outcome here is a classification of fraud or no fraud for each transaction. We can use this data to build a model that will classify new data accordingly, whether as fraud or not fraud. We'll explore the concept of classification using the default dataset. We are interested in predicting whether an individual will default on his or her credit card payment on the basis of annual income and monthly credit card balance. We have plotted annual income and monthly credit card balance for a subset of 10,000 individuals. This graph displays individuals who have defaulted in a given month in orange and those who did not in blue. It appears that individuals who defaulted tend to have higher credit card balances than those who did not. Looking at the dataset, we see that there are two inputs, annual income and monthly balance. These inputs are called features. Then there is one output called default, which is a response variable specifying whether an individual defaulted or not. The goal of any model is to establish the relationship between inputs and outputs. This is illustrated with the equation y equals f of x. F is the function. So y is the output, x is the input, and f of x represents a function of the inputs. In linear regression, the model generally takes the form of y equals beta plus beta 1 times x, or y equals mx plus c. For example, if we're trying to predict the price of a used car, which will be y, we can map the relationship of the mileage to the price where x is the mileage. So in linear regression, we can create a model based on the available data. The prediction model would take the form y equals mx plus c. Once we have the intercept and coefficient, we can now predict the price of a car based on mileage. So if a car has done 30,000 kilometers, we can predict the car price as 19,588. In linear regression, what we are trying to predict is always quantitative and on a continuous scale. Compare this to a situation where the output is not quantitative, rather it is qualitative. Example, here we have data for monthly balance and the output is categorized as yes and no for the default column. Logistic regression models the probability of an outcome. In this case, probability of default. For example, the probability of default given balance can be written as probability default equals yes if balance is given. As an example, our model predicts the probability of default as 62% for someone with a monthly outstanding balance of $7,500. Let's compare the outcomes with linear and logistic regressions. In linear, we have a prediction of 19,588 as the price of a car that has done 30,000 kilometers. In logistic regression, we get a probability of 62% for defaulting if the monthly balance is $7,500. So the difference is in the outcomes, wherein in linear, we get the absolute value, which is a continuous value, and in logistic regression, we get the probability of an outcome. The formula we use to calculate the probability is probability of x equals e to the power of b0 plus b1x divided by 1 plus e to the power of b0 plus b1x. This is called the logistic function. E is a mathematical constant and its value is 2.718. Beta naught and beta 1 are the intercept and coefficient. These are calculated from the training dataset based on a maximum likelihood method. Applying the maximum likelihood method on the monthly balance and default data, we get the intercept as minus 10.65 and the coefficient as 0.005. We can now calculate the probability of default for any balance amount given. For example, if the balance amount was $2,000, we can now estimate the probability of default as 58.6%. Take a minute to go through how this was calculated. Optionally, we can apply transformations to our formula to determine different items. With a bit of manipulation on the probability formula, we can determine the odds. Odds and probability are not the same. Odds refers to the probability of an event happening divided by the probability of an event not happening. Example, if the odds of winning a game was 5 to 2, then 5 divided by 2, which is the odds, is 2.5. This translates to a probability of 5 divided by 5 plus 2, which is 71%. Note that while the value of odds can be any number from 0 to infinity, probability will always be between 0 and 1. By taking the logarithm of both sides of this equation, we get another equation. The left-hand side is called the log odds or logit. We see that the logistic regression model has a logit that is linear in x. Remember that in a linear regression model, beta 1 gives the average change in y associated with a 1 unit change in x. In contrast, in a logistic regression model, increasing x by 1 unit changes the log odds by beta 1.